Hi there. Welcome to the analysis design of a flyback. This is video number 14, and I will discuss how to model a pulse width modulator. Okay, so that's the topic. It's going to be probably a long video, perhaps. So I want to give as much detail as possible. That way you can make your own spice model. Okay, so as the title says, I'm going to try and model from scratch, or at least from basic spice elements, the PWM. And I've listed the subcircuits of the PWM. And keep in mind that some of the PWMs can be very sophisticated. So what I'm doing here is more of a simplified. I'm leaving out some of the other bells and whistles. So this is the basic one. And I'm trying to keep it as basic as possible, but yet have enough detail to give you an understanding. So why am I doing a model? Well, if you recall, or if you watch video number 13, I went and explained how a PWM worked. I discussed the various subcircuits, the error amp, the sawtooth or the oscillator, the flip-flops, RS, T flip-flops in the north, and so forth. And I went in detail how they cycle, or how they step cycle by cycle. Okay, so I've explained it. So now what I want to do is I want to give you an opportunity to model this and have a spice model where you can go ahead and reinforce what I've discussed. I did forget to put one circuit here. Let's see. And I'll put it in here. An oscillator. Or you can call it a clock. Okay. And this oscillator, I'm choosing, since I designed the flyback with the switching frequency of 100 kilohertz, we'll go ahead and keep it at that frequency. Okay. So let's go ahead and go to the spice. Okay. This is a circuit. Some of you have requested for the spice models. I may have sent you this model. It's basically the flyback. It's the one that I've been using in all the lectures. It's a 12 volts, half an amp, input range of 24 to 34. Okay. I already showed you how to calculate the primary inductance, how to calculate the output. I haven't discussed how to set the capacitance. Okay. Probably in video 15 I'll go ahead and discuss that. Got my MOSFET here. It's being modeled by a switch. In this case, if you notice, it says SW MOSFET. Let me see if I can zoom in. That's the name of this particular model. And if you come up here, this is where I define the model. So it's a dot model, SW MOSFET switch. And then I define the turn-on resistance. In this case, it's half an ohm. And then I also define the off resistance, which is 100 megs. And VT is the threshold voltage, and VH is the hysteresis. So basically, with these two, you can calculate the high and low. The high would be the 3 plus 2, that would be 5. And the low would be 3 minus 2, which would be 1 volt. So it switches at 5, and it switches at 1. Okay. Now with Top Spice, it's a very powerful simulator. It has 30,000 uh, parts or models, and one of the model that is included is the model that was developed by Christopher Basso. Okay, and this is this model. It's the PWM CM2. CM means that it's a current mode. Okay, so it's a very nice model, very nice and compact, and you can define the period. The period would be the reciprocal of the frequency, and we can take a look at perhaps the Spice model or what it consists of by going at the output. And if you notice, this is the net list. I believe it comes up to here, and that. So that's the code associated with the PWM. And again, this is one that was developed by Christopher Basso. So we're going to develop our own based on the lecture that I just presented in the last lecture in part 15. And I'll just give you a demonstration of how this one works. It runs pretty fast. It's an accurate model, and usually it converges well. Okay, so here it is. I don't have to adjust the duty cycle. The PWM self-adjusts and varies the duty cycle until you get a 12 volt. Okay, so this is the PWM that comes with Top Spice. So we're going to go ahead and make our own. And I have save. Okay. Here is my PW pulse width modulator. Okay, and let me go ahead and let me see if I can go to step by step. Perhaps I can put these side by side, and I'll try to cover them. And at the end, anybody that needs or would like to duplicate this, they're welcome to duplicate it. If not, you can email me for the request for this file, so you can have a better feel of how a PWM works. Okay, so the first one is, let's cover this, would be the reference voltage. Okay, so the reference voltage here is represented by this. This is my reference voltage. It's basically just the voltage source, and I will set it to 2.5 because that is what is typical. Excuse me. I have seen some that are 5 volts, but for the most part, they will be 2.5 volts. Okay. And I add a resistor in series, and I connect that to my error amp. My error amp is the second subcircuit. Okay, and keep in mind that the error app is always connected to the positive side or the non-inverting side of your error app. So this is your error app. Okay. Now, I put a resistor and I connect this node to a capacitor, and I label this node as my slow. Actually, slow, let me rename it. I'm going to name it slow start. Okay. That's a very important feature to have in a PWM, in that when you start a switching power supply, they have a tendency of overshooting. So to circumvent that, you put a resistor and a capacitor. That way when this turns on, instead of turning on straight to 5 volts or 2.5 volts, it comes up slowly in a very controlled way, and it eventually ramps up to 2.5 volts. So what it does, it prevents overshoot of the power supply. Okay, so that's connected there. Now let's go ahead and examine this. This is the inverting. The inverting is typically labeled as the FB or the feedback. That input comes from your output. In other words, your output is always connected to this input via a voltage divider. Basically, what we are doing is we're sampling the output, and we're taking a sample of the output, and we're feeding it into the inverting side of the error amp. Now the error amp, it compares the feedback voltage from the output, and it compares it with the reference voltage. So this is your reference, and this is a sample voltage, and it develops an error output, which is output here. Okay, that circuit, or the output of the error amp, is then sent to a comparator, and that would be our third circuit. Okay, so this is the comparator, and I'll go ahead and label that as comparator. Okay, and that signal from the error amp will be routed to the inverting side of the comparator. Okay, and we use this little resistor divider network to make this voltage, when this goes to maximum duty cycle, we want to make sure that this voltage does not exceed 1 volt. So we have this size where when this goes to its rail, and it typically, since it's a UA741, this goes up to about 3 volts. So with this ratio, we end up with 1 volt here. Okay, so this error voltage is sent to the comparator. In the meantime, the non-inverting, if you look in here, is labeled iSense. iSense is the current from your MOSFET. So basically, when the MOSFET turns on, you got current flowing through your primary, and if you recall, it looks like a ramp. Okay, it looks like a sawtooth or a ramp. That voltage, or that current, then develops a voltage across this resistor. R8 is a current sense resistor. Okay, and we do a little bit of filtering, because typically the leading edge will have a voltage spike due to the leakage inductance. So what we do is we scale it, and then we'll filter it through this little RC, and that signal, keep in mind, that's the current signal. That signal is fed back into your comparator. Okay, so that's how we do that. Now keep in mind, this is a current mode PWM, pulse width modulator. And in the lecture, I said that a current mode pulse width modulator has two feedback loops. So this is the voltage feedback loop, okay, and this is the current feedback loop, okay. So these are the two loops that we're sampling from our power stages, okay. Those are what we're sampling, and we're feeding back into our pulse width modulator, okay. So then your comparator then compares the signal from the error amp and compares it with the ramp, and it produces a voltage that when the current exceeds the EA, it basically resets this flip-flop, okay. That signal is sent to this RS flip-flop, okay. And let me explain this a little bit. What I'm using here, if you notice, it doesn't have voltage rail, okay, because I wanted to keep the model simpler. So what I'm using is an ideal op-amp as a comparator. So basically this will give you infinite voltage and infinite voltage in both the positive and negative. And to keep it from going infinite, I put a resistor here, a 500 ohm, in a diode. That way, if this goes to infinite, this line will clamp it to 5 volts, and if it goes to negative infinity, then this diode will clamp this to a negative diode drop. So this line is restricted or clamped between negative 0.7 and 5 volts. So the reason I did that is because I'm using an ideal, and I'm using an ideal op-amp to simplify the circuit and make it run a little bit faster. Okay, so that signal is then fed to your RS flip-flop. Okay, so let's take a look at this side. So this would be the set and reset, and let me go ahead and I'll label this as the reset and this as the set. Okay, so this is just your regular RS. Okay, and if you look at this line, you'll see my clock. Okay, so let me go ahead and check off what we have covered so far. Here's the RS flip-flop. Okay, so basically it gets a signal from the clock, okay, and at the set, and the reset gets a signal from your comparator. Okay, so those are the inputs. So the output is then fed to one leg of the input NOR. Okay, that's this part, and we discussed one leg so far, and this is the clock. The clock, if you'll notice, it's 0 to 5, and I have a time rise of 10, fall time of 10, and then my pulse width, what I'm doing here, I put the curly brackets, and it's 1 divided by the frequency times 0.01. 0.01 means that I'm going to get a pulse width that is 1% of the switching frequency. So basically, you're going to have a real thin pulse or a very narrow pulse. Okay, so that's what this coefficient does. The 0.01, it multiplies the period by that. Okay, and then the period, of course, is 1 over the frequency, and then the number of periods, 1 gig. So that's the clock. So then that covers that part. And we've already covered this leg of the 3-input NOR, and that's another subcircuit, which is we'll discuss. And then we also look at the top leg of this NOR input, and if you notice, it goes to your clock. Okay, so that's another leg of the input NOR. And if you look at the bottom NOR, that goes to your toggle flip-flop. And let me go ahead and label this. It's a T flip-flop. Okay, it's a toggle flip-flop. And if you notice, the toggle flip-flop is made out of a D. The D is connected to your Q naught. Okay, and then your clear and preset, which is the PREB, are tied to VCC. Okay, in this case it's 5 volts. So the signal then is actually the clock. So the clock, keep in mind, is fed to 3 things. The clock is fed to this NOR. It's fed to the set of the RS flip-flop, and it is also fed to the clock of your toggle. Okay, so then these 3 inputs are fed into your 3-input NOR. Okay, so then that covers, covers the 3-input NORs. It's got the 3 inputs, covered the toggle, and then finally, if all the 3 conditions that I had mentioned in the lecture number 14, this should be a high, low. I'm sorry, it should be a low. We'll give you a high, and then low. Excuse me, it's the other way. High, low, yes. So if all of these are low, you're going to get a low here that gives you a high. And if this is a high, these turn on, and it routes 12 volts to the MOSFET. And when this goes low, this turns off, and what it does, this turns on, and it grounds your gate. So this is routed back to your gate here. Okay, so if you need, to clarify things, we can actually put a wire here instead of a label. And grab it there and connect it there. I believe, bring that up. Okay, so I think I have just about everything labeled. Now, another piece of information that's very important, especially if you're using TopSpice, you want to make sure that the state of this toggle is correct. So to define it, you put IS equals 0. So basically what it does, it sets your Q to 0. Okay, so once you have that, it looks like you have a complete pulse width modulator, uh, the only thing would be is to set the control loop. I've already gone through the previous videos how I selected these. If there's any questions, and if there's enough questions or enough people that want me to go how I selected these, I can go over that again in the next video, but I would have to get feedback from you guys. Okay, so in a way, I think everything's complete. Looks correct. I've already said that, and I'll go ahead and press run. It runs pretty fast. Okay, there you have it. So it's regulating. Here's the 12 volts. Okay, and it's 11, but 11 and a half. So what you can do is you can raise, well, actually make this a little bit higher, and yeah, you raise R4 and that will raise this voltage. Okay, and if you notice, it comes out really nice, very controlled exponentially. Okay, and the reason that does that is because of this cap and this resistor. Let me go ahead and basically, let's remove that cap. See what happens if we allow that voltage to come up straight very fast. It should have a overshoot. Let's see if it does. See, it's got an overshoot. Okay, so this would be your part of your self-start circuit. I'm sorry, it's a cap. Let me go ahead and label this slow start. Okay, run it again. It should come up very, no it won't. And the reason is because this should be a U. And now it should work. Now, what I want to do is I want to compare or show this, what's happening at the comparator. Okay, so this is where you get a intuitive feel. So remember, this is your iSense. I'll go ahead and put it right here. So we're going to look at the error amp voltage. Remember, this voltage is the feedback, basically the error voltage that is produced between the output and your reference, which is your voltage feedback, and then this is your current feedback. And we're going to look at what happens. And let me go ahead and take the V gate off. Gate. Okay. So here you can see that the yellow is the error amp and your V iSense is your current. So whenever the ramp exceeds the error app, it resets and basically turns off your MOSFET. Okay, and this is what I was trying to explain in the PowerPoint presentation in video 13, how this interact with each other. Okay, now keep in mind that during soft start or slow at the beginning, these are going to be maxed out. Okay, and should have been soft. Okay, I notice when I put this capacitor, the slow start, it's not slow starting. It still has this overshoot, and the reason is because I did not initialize it. So to initialize it, you do a IC equals 0. So now you have that, and let me set this back to 2. Let's rerun it. Okay, so that fixed it. Okay, and let me go ahead and plot this part. This is pin 14. That's a slow start, and I'm going to plot it here. So I'll add pin 14, and here you go. So if you notice, it comes out exponentially, just like a RC, and what it does, it helps circumvent or minimize the overshoot. Okay, so here you have it. This is a current mode. Let me go ahead. It's a current mode pulse width modulator. Okay, you can put this as a subcircuit and minimize the schematic layout and just replace it by a little box with the appropriate inputs, like such as clock, feedback, iSense, and so forth. So if you have any questions, or if you want to play with this model, you can email your request at rbola35618@aol.com. I hope that you have found this video informative, and thank you for watching.